So it's 6:25, so we can go ahead and get started here. Um, this one's not going to be that hard, but there's a lot of information to cover, kind of like the one over the weekend. So hopefully you had a chance to watch that. We're going to just kind of fly through this too, because I know you guys are at least familiar with pH. We didn't watch the one over the weekend. Okay, well, there was a video over the weekend, so you might want to catch back up on that. Yeah, so acids and bases is what we're talking about here, just to kind of introduce you to that. And really the first video is, it's a lot of material, but it's fairly introductory stuff. It's not. The thing that you might struggle with a little bit is the idea of conjugate acids and bases, and we'll talk about that a little bit today. Okay, but today we're going to talk about the autoionization of water, which sounds complicated, but it's really not, and pH scale, which I know you guys are familiar with from, at least from biology and a little bit from in here, from the lab, one of the labs we did last semester. All right, so autoionization of water. Water is amphoteric. Okay, and again, not a term you would know probably unless you had watched the video from last time, but basically it just means that water can act like an acid or a base, okay? Depending on whether it gives away a hydrogen or gives away a proton to something else, or whether it takes a proton from something else. It can actually do both. So because it's amphoteric, every once in a while in a sample of pure water, and I mean every once in a great while, it doesn't happen very often, but a water molecule can donate a proton to another water molecule. Okay, so that makes one of them H3O plus, and it makes the other one OH minus, because one of them now has one less hydrogen, the other one has one more hydrogen than water normally has. So this is called autoionization. And as you can see here, only about 2 out of every 10 to the 9th molecules does this in a sample of pure water. So it doesn't happen very often, which explains why water doesn't conduct electricity very well. There are a few ions in pure water, but 2 out of every billion, that's not nearly enough to conduct electricity, okay? All right, so basically we can write an equilibrium expression for this, or we can write an equilibrium reaction for this, I guess I should say. This first equation up here, more accurate, because that shows what's really going on. You've got 2 H2O molecules, and one of them is giving a hydrogen to the other, and so then this one becomes H3O plus, and the other one becomes OH minus. Okay, but you can also write it like this. It's very commonly written this way, and you'll start to see that as we go through this unit, that this is an acceptable way to write this. It's just kind of a shorthand way of writing it. As long as you understand, that's not entirely correct. I guess in the sense that it's not showing the whole story. Okay, so 2 ways you can write that, but at 25 degrees Celsius, the equilibrium constant for this reaction is 1 times 10 to the negative 14th. Okay, which again, let's just think back to what equilibrium constants are telling us here. If it's a really, really, really small KEQ like that, what does that tell you about the reaction? Okay, it's very reactant favored. In other words, this is the majority of what's in the solution, right? This happens every once in a while, but not very often, okay, which is what we were saying before. Water does not ionize very much, okay? But this equilibrium constant is actually important enough to get its own name, or own symbol, I guess. Kw, okay? The equilibrium constant for water, okay? So what you can say here is, again, if we write this equilibrium expression, now this is a little tricky here. When I'm writing this equilibrium expression, why is it that I only include those 2 things? Or these 2 things, depending on which equation we're using to write it. Remember, equilibrium expressions are products over reactants, right? Okay, the reactants are pure liquids, right? So we don't have to include those in our equilibrium expression because they're just kind of an understood constant 1. All right, so that's why this is the equilibrium expression for Kw, which means you can maybe see this. If we know the concentration of H plus in our solution, then we can figure out the concentration of the OH minus, right? Because, I mean, you know two of the variables, you can figure out the third fairly easily. And then Kw applies not only to pure water, but to any aqueous solution, which is nice because, again, what it means is if we know the H plus concentration, we can figure out the OH minus concentration. Product of those two will always be 1 times 10 to the negative 14th at 25 degrees Celsius. Okay. Remember, if we change the temperature, we change the equilibrium constant. So it's going to be different if it's not at 25 degrees, but most of these acid-base problems that you're given, we're going to assume 25 degrees Celsius. Okay. I say assume, most of them will say that it's at 25 degrees Celsius. I've never seen an acid-base problem on the AP exam that's not at 25 degrees Celsius. Because, well, I guess I should say I've never seen one where you actually have to use the KW, the equilibrium constant, because obviously that's the one they want you to know. Okay, so the H plus OH minus ratio here, that's really what determines whether something is acidic or basic or neutral, okay? If the H plus and the OH minus concentrations are equal, that's a neutral solution, okay? So even though water splits apart into H plus and OH minus, or H3O plus and OH minus, because they're equal in concentrations, the pure water is still exactly pH 7. It's exactly neutral, okay? If you have more H plus than OH minus in the solution, then it's acidic, which we kind of talked about that before. You know, you put hydrochloric acid into water. As soon as you do that, what happens to the HCl? It dissociates, right? So then we end up with H plus and Cl minus. This doesn't really do much in terms of the pH. The Cl minus doesn't. But the H plus obviously increases the concentration of H plus in the solution, and now we have an acid. Okay. You put a base into water, a base like sodium hydroxide. As soon as you put it into water, it splits apart, Na plus and OH minus. Again, the Na plus doesn't do a whole lot in the solution as far as the pH is concerned. The OH minus, we're increasing that concentration now, and we have a basic solution. Okay, so that's why you add this acid as base into a solution. It makes it more acidic or basic. It has to do with the H plus and OH minus ions. Whoops. All right, didn't realize that I already had stuff on here. Sorry about that. I'm gonna have to delete this over here. Okay, I'm gonna have to do that for a couple of these. Give me a second. Don't remember that number. Well, I mean, remember that. Oh, gosh. Okay, there we go. Okay. So, first example here says calculate the values of H plus and OH minus in a neutral solution at 25 degrees Celsius. Any ideas on that one? You may have an idea because you already saw it. Okay, concentrations are going to be the same in a neutral solution. That's kind of the key there that we need to remember. And we know that Kw is 1.0 times 10 to the negative 14th, right? And we also know that our equilibrium expression is just Kw equals H plus times OH minus, okay? So let's say that we call H plus X. Because these are equal, OH minus is also going to be X, right? So 1.0 times 10 to the negative 14th equals X squared, right? So take the square root of both of those. And that should be 1.0 times 10 to the negative 7th. Okay. So that's going to be the value of both the H plus and the OH minus, and this is going to be in molarity. When we're talking about a solution, you can assume that this Kw is K with respect to concentration. It would make no sense to talk about K with respect to pressure. Okay, indicate whether solutions with each of the following ion concentrations are neutral, acidic, or basic. So if the H plus concentration is 4 times 10 to the negative ninth, what do we think? Okay, so that's a smaller concentration than 1 times 10 to the negative 7th, right? So if that's the case, we probably have, well, we definitely have more OH minus in that solution than H plus, so A here is going to be basic. Okay, what about B? Okay, 1.0 times 10 to the negative 7th, that's neutral because that means they're equal in concentration. And then the OH minus concentration is 7 times 10 to the negative 13th. Okay, and you gotta be careful here, but you're right. Okay, so OH minus concentration is low here, very low. Okay, which means the H plus concentration must be high, so this one's going to be acidic. Okay, so that's kind of how you can tell just based on the concentration of one or the other of these. Calculate the concentration of H plus in a solution in which OH minus is 0.010 molar. Okay. So then again, we're just using that Kw equation, 1.0 times 10 to the negative 14th equals H plus times 0.010. Okay, and you're just solving for H plus. So divide both sides by 0.010. And your H plus should equal, I should be able to do that in my head. Is it 1 times 10 to the negative 12th? Is that right? Alright, so, and we can talk about that again. Acidic or basic solution? That's a fairly basic solution, right? Because the OH minus concentration is so much higher than the H plus. And then B, a solution in which the OH minus is 1.8 times 10 to the negative ninth. And again, we're assuming temperature is 25 degrees Celsius, okay? So on this one, again, we've got the 1.0 times 10 to the negative 14th is equal to, again, we're solving for the H plus here, times 1.8 times 10 to the negative ninth. Now this one would be harder to do in your head. But you just take the 1 times 10 to the negative 14th divided by 1.8 times 10 to the negative ninth, and you end up with 5.6 times 10 to the negative 6th. Okay? Alright, usually the H plus concentration is really small, so it becomes a pain sometimes to be dealing with numbers that are that tiny all the time, having to write it in scientific notation, all that stuff. So that's why the pH scale was developed. Okay, the pH scale kind of helps those numbers to be a little more manageable. We end up with numbers that are usually between 0 and 14. Okay, so it's much easier to work with. So to find the pH of a solution, you take the negative log of the H plus concentration. Did you guys learn that in biology? Okay, I guess not. Alright, I didn't know how in-depth they went about pH. Probably just they talked about the scale and what 0 to 7 tells you and what 7 to 14 tells you. But it's actually related to the H plus concentration. Okay, so the pH of a neutral solution, negative log of the H plus concentration, which is 1 times 10 to the negative 7th, which, what does that end up being? Yeah. Right? I mean, you know a pH 7 is a neutral solution, but if you punch negative log of 1 times 10 to the negative 7th into your calculator, you get 7. Okay? So that's why a neutral solution is 7, is because that's when you have equal concentrations of H plus and OH minus. Okay. For an acidic solution, the pH is going to be lower than 7. So an example here, H plus is 1 times 10 to the negative third. Okay, that's a higher H plus concentration than your OH minus concentration in that solution. You take the negative log of that, you end up with 3. Okay. Now notice here with these easy examples where you just got 1 times 10 to the something, this exponent actually matches with the pH. Now that only works when you have 1 times 10 to whatever it is. Okay, if this is a different number than 1, then you're gonna have to punch it in your calculator. Okay, but same thing over here for a basic solution. The H plus example here is 1 times 10 to the negative 12th, so the pH is 12. Okay. Alright, just an example of some things, and I'm sure you talked about this in biology, but where some things fall on the pH scale. This is kind of fun. 1 molar hydrochloric acid has a pH of 0. Okay. What does that tell you about 12 molar hydrochloric acid? Things can actually have a negative pH. That is possible. Okay. Usually things fall in the range of about 0 to 14. Now what you can tell here is that you can kind of see how they developed the pH scale, right? HCl 1 molar was used as kind of the standard starting point. They said that's going to be 0. Anything more acidic than that, it's going to be negative on the scale. Okay, and then they said 14 is going to be 1 molar sodium hydroxide. That's our standard for the high end. Anything more concentrated than that is going to be above 14 on the pH scale. Okay, so 0 to 14 is not. Your substance doesn't have to fall between those two numbers, but most things do. Okay. Your gastric juice, in other words, your stomach acid, is about 1.5, somewhere between 1 and 2, so fairly acidic. Orange juice is close to a 3. Coffee is about a 5. Milk is just right around neutral, but slightly acidic. Blood is slightly basic. And then you've got all your household cleaners and stuff that are fairly basic. Okay. That's the kind of stuff that you probably don't want to drink. Notice, most of the things that we, drink or eat, they tend to be weak acids rather than, bases. Okay, estimating pH values. So we've got an H plus concentration of 0.050 molar. Now, again, this is not hard. You're just plugging into the formula we just talked about, right? pH is equal to the negative log of the H plus concentration, okay? So in this particular example, negative log of 0.050. Oh, and I should mention this as well. Again, we're taking the log of something, so that makes pH a unitless number. Okay, there are no units for pH. Negative log of 0.05 is giving me a pH of about 1.3. Okay. Alright, another sample problem. Calculate the pH values for a solution in which OH minus is 0.010 molar and a solution in which OH minus is 1.8 times 10 to the negative 9th. Alright, this is slightly more tricky. Why is this tricky? They're giving you the concentration of the OH minus, okay, and pH is the negative log of the H plus concentration. So the first thing we get to do is figure out our H plus concentration on both of these, okay? So for A, it's 1.0 times 10 to the negative 14th is equal to H plus times the OH minus, which is 0.010. Okay, and again, this one, you can probably figure this out. The H plus is 1 times 10 to the negative 12th. We've already done this one. Okay. So then you take the negative log of that, and you can do this one in your head, right? Negative log of 1 times 10 to the negative 12th? 12. So the pH is 12 on that one, okay? And then you just want to check and make sure that kind of makes sense because the OH minus concentration is relatively high here, right? So we would expect this to be a basic solution. All right, and then for B, same thing, I'm going to skip writing it down this time, but you take 1 times 10 to the negative 14th divided by 1.8 times 10 to the negative 9th. That gives you an H plus. We've already done these numbers, haven't we? I used these on earlier example. I just realized that. So then we take the negative log of the 5.6 times 10 to the negative 6th. That one will be a little bit harder to do in your head. And you end up with a pH of about 5.3 or so. And again, just checking to see if that makes sense. The OH minus concentration is less than 1 times 10 to the negative 7th, right? So we would expect this to be an acidic solution. In an acidic solution, the pH should be less than 7, and it is. Okay? All right, sample of freshly pressed apple juice has a pH of 3.76. Calculate H+. Oh, now this gets a little more interesting. How do we do that? Okay. Do you remember, we talked about this when we were talking about natural log, right? How to solve for these natural log problems. If you got natural log of x, you e it on both sides. You take the e of both sides. Okay. Log has a base of 10. Natural log has a base of e. That's why you take e to the whatever power to get rid of that natural log. To get rid of a log, you just 10 it. Okay? So 10 to the 3.76 is equal to, 10 to the negative log of the H plus concentration. Okay? And so when you take 10 to the 3.76, I take that back, I apologize. Let's simplify this a little bit first, okay? This negative log makes things a little bit weird, so I'm going to divide both sides by -1 first. Okay, so I end up with negative 3.76 equals the log of the H plus concentration. Okay, and then when we 10 it, things are a little bit more normal. All right, so now we've got 10 to the negative 3.76 is equal to, when we 10 this side, it just becomes the H plus concentration. Essentially what it does is it gets rid of the log. Okay, so then 10 to the negative 3.76. That's going to give you a pH, an H plus concentration of 1.74 times 10 to the -4th. Okay, which again, it's just good to check and make sure that your answers seem reasonable. Okay, that's a fairly, it's a higher concentration of H plus than 1 times 10 to the -7th, right? And our pH is 3.76, so both of those would point to the solution being a little bit acidic. All right, that makes sense? All right, we can also figure out the pOH scale, okay? And the pOH is the negative log of the OH minus concentration, okay? If you take the negative log of both sides of the Kw equation, so we've got Kw is equal to, well, here, let me actually write the number for this one because we know the number here. 1.0 times 10 to the -14th is equal to the H plus times the OH minus. Okay. If we take the negative log of both sides of this thing, the negative log of 1 times 10 to the -14th ends up being 14. 14 equals, now this is a little bit tricky, okay, you'd have to remember this, but when you take the negative log of something times something else, you actually end up adding those two things together, okay? So it would end up being, we could rewrite this as the negative log of H plus the negative log of OH minus, okay? I should put my parentheses on the other side. That's a little confusing. But that's what happens when you take the negative log of something times something else, okay? If you have, hopefully you remember this from math class, the log of x times y is equal to the log of x plus the log of y. Right? You guys remember that? Okay, so that's essentially what we're doing here, right? Now, what's the negative log of the H plus concentration? What is that when we find the negative log of the H plus? What are we finding? Well, okay, that is the concentration of the H plus, right? Remember, when we take the negative log of the H plus, negative log of the H plus concentration equals what? Yeah, the pH, right? Okay, so 14 equals, this is the pH, plus, and what's the negative log of the OH minus concentration? The OH. Okay? So that's kind of a useful equation. If you add the pH and the pOH together, they should equal 14. Okay? Which, you might have already just intuitively sensed that that was going to be the case. But you take the pH plus the pOH, and that adds up to 14. Okay. If a beaker contains 0.2 molar HCl, what's the pH of the solution in the beaker? Why did I put this on here? I mean, this is very similar to what we've just done, right? I guess the only trick on this one is it's actually talking about putting HCl into solution. But, I mean, we've talked about this enough that hopefully you realize this is going to be a 1-to-1 ratio when it splits apart, right? So it's still going to be 0.2 molar H plus concentration. All right, now you got to watch out for that if it was something like H2SO4, okay, and we assume that that completely dissociated, then we'd have a different story, okay? But for something like HCl, 0.2 molar HCl is the same thing as 0.2 molar H plus once you put that in the solution, okay? So you just take the negative log of that, and that gives you the pH. If a solution has a pH of 8.25, what is the OH minus concentration in that solution? Okay, so again, these are just sort of the ins and outs of things they might ask you about pH and what you might have to find. So again, we've got 8.25 is equal to the negative log of the H plus concentration. And after a while, you're going to start to see that what you essentially end up doing here is you take 10 to the negative whatever number is over here, right? So the H plus concentration is going to be 10 to the negative 8.25, whatever that is. 5.6 times 10 to the negative 9th. And that's the H plus concentration, okay? So then to find the OH minus concentration, you'd use the KW equation. 1.0 times 10 to the negative 14th is equal to 5.6 times 10 to the negative 9th times the OH minus concentration, and then just solve for OH minus. Okay. I'm getting 1.8 times 10 to the negative 6th. And again, we just want to check and make sure that makes sense, okay? This is fairly close to a neutral solution, but it's a little bit basic, right? Because it has a pH higher than 7. And that makes sense because the OH minus concentration is a little bit more than 1 times 10 to the negative 7th. Okay. Here's where it gets a little bit trickier. 50 milliliters of a 0.1 molar CaOH2 solution is diluted with an additional 50 milliliters of distilled water. What's the new pH of the solution? Okay, in order to find the pH of this solution, what are we going to have to figure out? Right, the OH minus concentration in the solution, right? All right. So let's think about this. Problem here is, well, there's two problems really, okay? When we put this CaOH2 into water, what's it going to do? It's actually going to completely dissociate. This is an ionic compound that does dissolve in water, okay? So it's going to completely split apart. Well, the thing is, when it splits apart, there are going to be 2 hydroxides for every 1 calcium, right? So let's figure out what the dilution does to the concentration of this first. I think that's the easiest way to do it. And then we need to realize that the OH minus concentration is going to be twice the concentration of the CaOH2. Okay? because of the dissociation that happens. So what's the easiest way to figure out what our new concentration of calcium hydroxide is going to be after we dilute it? Okay, so it just kind of makes intuitive sense that the concentration is going to be cut in half because we're doubling the volume here. All right, now, if the numbers weren't quite so easy, you guys remember that formula? Okay, that's our dilution formula that we haven't talked about in a long time. Okay, but M1V1 equals M2V2. So you've got your initial molarity here. That's what the M stands for. Times your first volume, which is 50 milliliters. You do not have to change that into liters because it's just a ratio. Okay, and then we want to know what our new concentration is going to be. So that's our variable here. Times, what's our new volume? 100, right? You have to be careful there. We're adding 50, so our new volume is 100. All right, and ultimately that's going to have the effect of just dividing the concentration in half. So our new concentration now is going to be 0.050, right? Molar, and that's the CaOH2, right? This is kind of funny. You actually could not realize, you could make two mistakes here and come up with the right answer. Because then, what does the OH minus concentration end up being here? Double this number, which we just halved, right? So, actually, if you forgot both of those things, if you forgot that this is going to be twice as concentrated because it dissociates into two OH minuses, and you forgot to account for the dilution, you'd actually get the right answer. That's not usually going to happen. Okay, so there's our OH minus concentration in that solution, right? We want to know what the pH of the solution is, so I think probably the easiest thing to do here is just take the negative log of that number. And the negative log of 0.10 is going to give us, I mean, this is essentially 1 times 10 to the negative first, right? So that's going to give us 1. But what is that? We took the negative log of the OH minus concentration. This is the POH, right? Okay, and then we just have to remember the POH plus the pH equals 14. So the pH is 13. When you're given an OH minus concentration, I think that's probably the easiest way to get to pH. Just take the negative log of that. The problem with that is sometimes it's easy to, get this and then forget that you need to subtract it from 14. Okay. All right. pH of a 0.1 molar solution of NaF be greater than, equal to, or less than 7. We're going to skip that for now. I forgot that was on there. We're going to talk at the end of this unit about how salts change the pH of a solution. I don't think we're quite there yet. Okay, so we'll come back to that. All right, another one. How could 500 milliliters of sodium hydroxide solution with a pH of 14 be changed into a solution of NaOH with a pH of 11? Is that one on your sheet? Really? Oh. Where are we on the sheet? Back page. Okay. I'm gonna. Well, this is a tricky question though, and I'm not sure where else that might show up. So I think we probably need to talk about it. Tell you what, we'll finish the rest of the notes and come back to that at the end. Okay. All right. So measuring pH. This is pretty straightforward. We have already measured pH this year using pH meters, right? They weren't the best pH meters in the world. I wish we had better ones, but they use electrodes, okay? And those electrodes actually measure voltage, okay? Which varies with the pH of the solution, so it can actually measure how much how many H plus ions there are in that solution, depending on, the voltage in the solution. You can also use indicators, which we've also used. Do you guys remember the name of the indicator that we used for the titration lab we did? It starts with a P. Close. Yeah, phenolphthalein. And it's got that weird, it's like phenolphthalein is the way it's spelled. It's got that weird spelling to it, okay? So that's one. There are a bunch of other indicators that you can use. Cabbage juice is actually a really good indicator, which is very strange. But if you take a cabbage, purple cabbage, boil it in water, okay, that juice that comes off of it when you boil it, you can actually use that. It will turn a bunch of different colors based on the pH of whatever you put it into, or you put into it. Okay, so that's kind of a neat little thing you could try at home. So here's an example of some different indicators, and obviously what you want to change, or what you want to pick here, is an indicator based on the pH change you're looking for. Okay, now why would we ever want to use an indicator that doesn't change at 7 or close to 7? Because isn't that when things change from acidic to basic? Well, actually, not necessarily. I know that sounds weird, okay? But sometimes the H plus and the OH minus concentration will be equal at pHs that are not 7, okay? We're going to get into that when we start adding weak acids to strong bases and strong acids to weak bases and stuff like that, okay? Which will be more in the next unit. We'll talk a lot about titrations of those sorts of things. Okay, so which indicator would be best to use for an acid-base reaction where the equivalence point would be reached? And again, well, we've talked about equivalence point because we did a pH, or a titration lab. Do you guys remember what equivalence point means? Same amount of concentrations of what? There you go, H plus and OH minus, okay? So the equivalence point is when you have equal concentrations of the H plus and the OH minus, all right? So which indicator would be the best to use for an acid-base reaction where the equivalence point is reached at a pH of about 3.8? What do you think? Probably methyl orange would be our best choice there because that's right where it changes from red to yellow, right? So you want to pick an indicator that changes color right when your equivalence point is reached, okay? All right, so let's go back to that other one because I want to talk about this. This is a tricky question, all right? But we can figure this out. So you've got 500 milliliters of sodium hydroxide, and it has a pH of 14, okay? What does that tell us about the concentration of the OH minus at this particular point? You could actually look back a little bit in the notes and see. Let's see if I can get back to it. Look at that. 1 molar sodium hydroxide is a pH of 14, right? Okay. So I cheated a little bit there. I mean, we could figure that out based on taking the, the negative log of that number, okay? And so negative log of that, or I'm sorry, we could 10 that, right? Because this is the negative log. So 10 to the negative 14th, that would be the concentration of the H plus, which means the concentration of the OH minus would just have to be 1 at that point, okay? So the OH minus in this initial solution here is 1 molar. Okay, but we want to change it into a solution that has a pH of 11. Well, what would the OH minus concentration be in a pH solution with a pH of 11? This is a little bit trickier, okay? Let's do this kind of in reverse here. What's the pOH of a solution with a pH of 11? 3, right? Okay, so the pOH here is equal to 3 because they have to add up to 14. All right. So if I want to find the OH minus concentration, then I'm going to take 10 to the negative third. I have to 10 this number, okay? So, I mean, essentially it's going to give me 1 times 10 to the negative third molar. So here's my first concentration, here's my second concentration, right? I want to change it from this to this. I want to dilute it. What might I use? What equation? M1V1 equals M2V2, okay? Alright, so again, I've got my initial concentration is 1 molar. What's my initial volume? 500. You know, I think I made up this example, and I think it's going to give us a ridiculous answer. I think I remember that from last year. My second concentration here is 1 times 10 to the negative third. So I'm solving for V2, okay? So take 500 divided by 1 times 10 to the negative third, and you get 5 times 10 to the fifth milliliters, okay? Which actually, we can divide that by 1,000, and it's not quite such a ridiculous number. It's the same thing as 500 liters, okay? But, I mean, still kind of a ridiculous number, right? But what we would have to do here is you would have to add this solution, dilute it down to 500 liters, and then you would have a solution with a pH of 11 instead of a pH of 14, okay? All right, that's it for today. We'll see you in class.